So we were talking about mutex locks, and this is certainly supported in many different languages. And in Python, they certainly follow this convention. So you could do import threading, and then you can do a lock by calling threading, which is the package name, dot lock. That's a constructor call. So lock is a class, so you instantiate a lock. Once you have the lock, you can call acquire release on it. Okay. And in fact, it gives you another option of blocking equals to true or false. Okay, so by default, if you don't specify blocking option, then it would be blocking. So acquire wouldn't return to you until it actually acquires. And most likely, that's the intuitive behavior. But you could also do trying to acquire, so blocking equals false. And then in that case, it would not block, but you can check to see if you successfully got the lock. And release will be unlock. Okay, so that way. And in fact, you can call this l.release on any lock, not just the original thread that unlocks it. Okay. Okay. So now semaphore. This is one of the most important topics ever in OS. Even 10, 20, 30 years from now, this is still going to be an important topic. You definitely will get questions, and more than one question on semaphore. So what's a semaphore? Well, a semaphore originally, that's not what it means in OS, but originally it's a way to encode symbols using two flags. So this was before radio communication or other forms of communication. People were just using flags to say A, B, C, D, and I spell out words using flags. Of course, you can use binoculars, or you have good eyes, you can probably see. Okay, and that's how they sent messages before, say, maybe telegrams. And so, but this is not what semaphores are in computer science. So when we talk about semaphore, we're talking about semaphore invented by Dijkstra, not Dijkstra. It's a Dutch word. So IJs is pronounced A, everybody pronounces I, so it's Dijkstra, okay? So I'm going to ask you about the pronunciation. Don't pronounce it as Dijkstra, no. It's a very famous computer scientist who passed away just not that long ago, 2000 something. And did a lot of pioneering work, and you probably have taken the algorithm, Dijkstra's algorithm. Yes, right? It solves the problem of shortest path, yes. And so, yeah, very famous. And of course, he also contributed big time to operating systems. And they were building one in the 1960s called the multiprogramming system. Okay, kind of a funny name, but okay. And the purpose is to come up with very simple mechanisms for supporting synchronization. Why? Because they actually ran into these race conditions and all sorts of nasty problems. Got to do something about it. So they came up with, Dijkstra, came up with two primitives. And when I was a student, we call these P and V. What? P and V? Okay. These were Dutch words. P was probe. Are there any Dutch students here? Don't want to mispronounce it. Proberen, or that's like English word probe, or to test. And V is verhogen, I guess, to increment. So really, you can think of it this way. So P is to wait. That means I want to borrow something. And V, signal, that means I'm returning something. Okay? And this is used in shared resources. So you can think of it as, library has books, right? If I want to check out a book from the library, I do a P. And then that's a request. And if there's a book available, great. I grab it. I don't have to wait, start reading. But I go and I wait, right? Wait until somebody returns the book, right? So that's kind of how it works. And then and V is, okay, I'm done reading, returning. So it increments the count. That's why that, okay? And they no longer call these P and V anymore. They call these wait and signal. But still, the book includes this, so like old-timers like myself can, what? Because if you look at PMV, it's not making much sense. So programmers used to have more limitations on how many letters they can have on the variable names or function names. That's why there's create is just create, not a, they're missing the E to fit. And now that's not even an issue. So let's use just more informative terms. And these are now standard terms, okay? So P is now called weight, V is now called signal. Okay. Now, so what is semaphore? So in very simple terms, a semaphore is just an integer. It counts the number of resource instances. So for example, in the library, a resource might be, say, a book. And there might be like 5 copies of the same book, right? And so it might be initialized to 5, that count, right? And if somebody calls a weight on the book, well, they don't actually weight, they call a P on it, right? So they check out a copy, now that gets decremented to 4, and okay, they go. And second person comes, grab another, it goes down to 3, 2, 1, and 0. And then what if the next person comes? Well, they don't get the book, right? But that count goes down to negative, okay? And so that is that count. So you can think of it as if it goes to negative, that means there's somebody waiting, okay? And signal is when somebody returns a book, and then that increments. But there could be still a waiting list. There's still people waiting. So that means even if that count is negative, it's still possible for somebody to get a book, right? Because as soon as one person returns a book, then the next person in line gets it, right? So it doesn't depend on the count being non-zero, okay, or positive. And very important, weight and signal should be paired up, just like their lock and unlock should be paired up, right? So that means if you check out a book, you better return it, right? And otherwise, you don't get to graduate or something. Anyway. Okay, so now there are two ways of implementing a semaphore, just like locks. You could do busy wait, or you could do more with a non-busy wait version, which means you get on some wait list. So busy wait just means it's a lot like polling. So wait looks like this. While s less than equal to 0, you do busy wait. And so what does that mean? That means right now, the library, you want to check out this book, it's showing 0 or negative, right? That means no more copies available, and or even there's somebody already waiting, right? So you just have to busy wait. But then when you get out, the S is then, so by the time you get out, then S gets decremented again, right? So that means one copy became available, and so in this case, S became temporarily maybe 1 or above 0. But then I grab it again, right? Because I wanted to check it out. So that's why it's followed directly by the S minus minus, okay? Now signal, originally called V, that just means I'm returning the book. No need to wait, just drop it and increment. That's like that, okay? So you can think of it as a generalization to a lock. Whereas a lock just does mutual exclusion, only one person can hold a lock at a time. This allows you to have multiple people all checking out resources to use, okay? So this is a generalization. So it does achieve some locking effect. And in fact, you can use a semaphore to implement a lock, okay? Now, this is a busy wait version. It can be inefficient, but arguably, for the same reason as polling. So you could do a non-busy wait version by putting somebody on the wait list, okay? So what can you do? So now semaphore is very flexible. Counting semaphore is what we talked about, like 5 copies of the same book at the library. So S is initialized to some n, in this case 5, for 5 copies. And so 5 instances or n instances in general. So that's what you initialize it to. Or you could do binary semaphore by initializing to 1. And guess what? That is a mutex, right? Because mutex means there's only one thing. Somebody grabbing it excludes everybody else, right? So that's a single copy. You can do barrier by initializing S to 0. It's like, what? Really? Yes. So how does that work? So that is actually a funny way to use semaphore mechanism. But what's barrier? Barrier just says you want to enforce what's called a precedence order. So A must happen before B. So in general, but A and B are done in 2 different processes. So how do you do that? Well, you set up a barrier. So if A comes around, then it lifts the barrier, and then when B comes later, said, oh, no barrier, it doesn't have to wait, just keep going through. But what if B arrives, and then it's from separate process, and then so I'm about to do B, but can I do B? No, A hasn't been done yet, so it hit a barrier. So A has to finish and lift that barrier, and then B can continue. Okay, that's what barrier means. So a semaphore initialized to 0 can be for that purpose. Why? Because think of it this way. If A comes, B hasn't come, then it lifts the barrier by calling a signal, right? So it lifts that barrier. So when B comes later, oh, no barrier, it just goes through, right? But if B comes and says, oh, I see it 0, that means the barrier is still there. And then it has to wait for A to come, lift the barrier, and then B can go through. Okay, so that's how that works. So that's why it's initialized to 0. So temporarily, by lifting it, it goes up to 1. And then, right, so that's how it works. Or if in the case of waiting, it actually goes from minus 1 to 0. Anyway, so you can do busy wait or non-busy wait. And you could do a real-life example for semaphore in terms of parking lots. You see these parking spaces available, right? You go parking, 106 spaces available. So that means you should be able to enter. But if it hits 0, then you got to wait for some cars to come out, right? So every time one car comes out, it increments. So that's another example. And normally these don't show like minus. These available, they don't show minus because a lot of times they don't even let you take a ticket. So they don't have a way to register that, okay? And so 0 means it's full and nobody waiting. But a semaphore could show a minus 5. Okay, anyway. So that now, so for blocking and non-blocking, so you wait in line or whoever grabs it first, or is there a priority scheme in here, right? So now these are all open questions. So parking lot illustration. Now, you do notice if you are doing the busy waiting, the count actually never gets below 0. Or does it get below 0? Yeah. Well, it could actually get below 0. Okay, never mind. So value here, right? So, but you can see this as value. So 5, and then simultaneously you can have in the same time step a number of cars arriving. So arriving, so that means you can think of it as they take a ticket and then now down to 4, and then there's a spot. I have 5 parking spots, and then they park it, and then 3 more cars arrive in this next minute, and then so they take 3 tickets, now down to 1 spot available. They found the places to park, and subsequent ones coming in, 3 more cars, now you have a deficit of 2 because 1 car comes in, 2 has to wait, right? And then another one comes in, takes another ticket, minus 3, right? Wait, and then one car would depart, right? So car 0 leaves, makes a spot available. So next car comes in, and then another one arrives, right? So you can see how the count gets updated over time. Okay, so in this case, there's one counting semaphore for controlling the number of spaces. That's more of an admission type of condition. Now, individually, you may want to have a mutex or a lock on each parking spot. It's not explicitly shown here, but really only each spot should be taken by at most one car, right? So if you don't have a mutex, 2 cars would try to grab and squeeze into the same spot, and that would be bad. So yes, this would highlight the case where you might need 2 levels of synchronization primitives, one for admission into the lot, the other for each individual spot. But again, depends on how you implement this. Okay, so barrier, we talked about this. So if you are the one that should go first, what you do is you execute. So in this case, if you want S1 to go before S2, then do S1, do the signal, which lifts the barrier. And then for the S2, you wait on the barrier to be lifted, and then you proceed to S2. Do you have a question? You're talking about the parking lot spot. Yes, that's exactly right. Yeah. Okay. Now this is really to enforce precedence order. So anytime you see a semaphore initialized to 0, that's a barrier. Okay. And so this you can actually generalize this to like a DAG. A DAG is directed acyclic graph. So you should have seen this in your algorithms courses. Now, to every single precedent dependency can translate into a semaphore or barrier, right? And then whoever goes first basically does a signal after they're done, and whoever has a dependency has to go after somebody else. You do a wait on that barrier before you execute your part. Right? So in this case, P1 does S1 first and then signal A, signal B. Just tells these two, okay, I'm lifting your barriers. Now P2 does a wait on the barrier A to be lifted before you can do S2. And then when it's done, lift the barrier for C3 and so forth. Okay, so that's how you can do this. And these can all be spawned in parallel, but the barrier will take care of who can go, and just by using barrier synchronization. In process critical section, so this is where you want to prove that the critical section property still holds in terms of the semaphore, right? So in the case of weight of mutex, that's to say I want to enter a critical section to do that, and then signal mutex. That's to allow somebody else to then grab this lock. Remainder, so it makes progress, yes, assuming your critical section is a bounded amount of time. Now, but what about bounded weight? Because if you have multiple processes, well, we haven't said anything about in which order they should be allowed. I mean, parking lot, you might say, okay, people get in line, and eventually, yes. But in general, on an OS, you have priority scheduling, you have all sorts of things. You mess up with their ordering, maybe for good reasons, for optimize, but then that doesn't mean all of them will have bounded weight. Some of them could starve. Starvation is a problem, and we'll see starvation problem many times, including one that comes up later in chapter 7 when we talk about monitors. So semaphore without busy wait would look like this. And I'm using a mix of C and Python pseudocode to do this. So basically, remember what a PCB is, process control block. Basically, that's the struct for saving the state of each process. And these are often structured as a linked list. So you have a link to the next one, and then they go on. Okay, and then of course the semaphore would have its value. Now, instead of just using an int variable, you put it inside a struct, and then you keep a linked list. And so wait would do this. Wait would then do the decrement of this value, right? So minus equal to 1, that's decrements it. And if s dot value is less than 0, what does that mean? That means, there is not enough resource. So I want to check out a book, but I can't, right? So then I can put myself on a wait list. That's what it is, right? Maybe there's a sign-up sheet or something. So this s dot waitlist dot append of this process. So somehow I'm assuming I have access to like current thread ID, right, or a process ID, me, and then sleep. Now sleep is this pseudo statement in that it basically says go on to this essentially wait queue, right? So a lot like I/O. Okay? So that means upon context switch, it's not going to come back and try to wake up someone who's on a wait queue. But if s dot value is not less than 0, what does that mean? Well, it was first decremented, and if equal to 0, what does that mean? That means yes, I got the last copy. So. Right? If it's equal to 0, and if it's more than 0, even better. I got the copy, and somebody else can still check out the book, right? So that means I didn't have to wait. Right? So no need to even put myself on the wait list, right? Now signal means I'm returning the book, so the value gets incremented by 1. Okay, but in this case, what has to happen? Well, so if value is less than 0 or less than equal to 0, and this is after I increment back, right? So that means, oh, somebody still wants to read the book. They're on the wait list. So call them up, find the next guy. Hey, here's the book, right? So DQ them from the wait list, wake them up, and then they have the book. Okay, so that's what the non-waiting, non-busy wait does.
Make sure the interrupt doesn't happen when you.
Good question. Yes, it has to be atomic, but not when you're busy with. Yeah, good question. That's right. Yes, interrupt happens. No, this is not gonna work. So, but I mean, it's the same thing with your lock anyway, right? It has to be done atomically. Okay, so semaphore without busy wait, so that means the process linked list is kept track of as part of the semaphore. And you assume these are system calls, right? So sleep, a lot like yield, except when you context switch, if it's sleep, you don't even consider switching to it because it's not ready. And wake up means basically moving it from that wait queue to ready queue, so it can be scheduled sometime, right? So how do you select? Well, depending on the policy. Okay? So busy wait or not, you might say, hey, I think not busy wait is a good idea, right? Well, like that question that was just asked, it has to be done atomically. And anytime you have to do atomic operation, it costs you something. It's not trivial amount of work, especially if you're running on a multiprocessor, multi-core architecture, which is now mainstream. So, and also considering the fact that a lot of these critical sections are actually quite small. Okay, I mean, critical sections can vary from something very small to something very big. So if you're dealing with something that's rather small, then it's probably not worth it to even do a non-busy wait version, or to get on the wait queue. Why? Because, well, chances are I run through, I don't even have to wait, right? So it's just like I have a little. You're trying to check out a book. It's only like it's a leaflet, like 5 pages. Most likely, somebody looks at it, okay, I'm done, and then return quickly, right? And so, is it worth it for you to get on the waiting list? Probably not, because if you just sit around for a little longer, they're done, and then you can grab it quickly, right? Whereas sometimes you have these critical sections that can take minutes or hours. Well, yes, obviously you want to get on some wait list instead of polling for hours, right? That's just not worth it. So, and especially for multiprocessor, anytime you want to do an atomic operation, it's just inherently more expensive. Okay, but if your wait is long enough, then yeah, you can amortize that cost very well. Okay, so this just goes to show it's not always better to do the non-busy wait version. Sometimes polling may just be the better answer. Okay. Now semaphores, great, right? And you can do everything. It can be used for barrier, it could be used for mutex, it could be used for n counting semaphore, n resources, right? So many other things. So what's wrong with them? Nothing wrong. It's just they're a little too low level. It's like, ooh, a little scary to use. And they're two separate calls. So if they're not matched up, then just like somebody who checks out a book and never returns it, or what if somebody never checked out a book and returned a book and pretending it to be a library book? Now you have 6 copies instead of 5. That really confuses the heck out of that librarian, right? So, but who's to prevent you from doing that, right? So that programmer better behave, or else can mess up the system. So these things need to be matched up. Yeah, and the proper way to do it most of the time is you wait first, then signal. But barriers do it the other way around, or could do it the other way around. And in fact, they do it in 2 separate processes. One process does the signal, one process does the wait, because it's lifting the barrier for another process. How can anybody check across processes, right? Unless you develop a separate tool and then there's program analysis and all that. Otherwise, it's very difficult, right? You just have to kind of trust them. And so this matching is not just something you can do textually. Like in Python, you do the with statement. Yes, it's there to ensure that by the time you leave that, it returns the resource. No, if you do a cross process, you can't. In general, it's an undecidable problem, right? So who enforces the pairing? And if you call too many waits, too many signals, could break the critical section. And if you call wait before signal, it could actually cause resource hogging. And what if you call these waits on different resources in certain order? You could actually get into deadlock. And that's a problem we'll be seeing in upcoming chapters, or 2 chapters from now. Okay, and those are really nasty problems, but people have done analysis to detect and even try to undo this kind of thing that causes deadlock. So these can be very nasty if you're not careful. Okay. Next is monitors. So monitors are more programming language level concepts, and this came around the time when object-oriented programming was starting to become a thing. So what were some examples? So early ones included Module 3. Later, there's like an object-oriented version of Pascal. Certainly, Java is big on the object. In Java, they don't have any globals or don't have top-level function. Everything is wrapped inside classes, and you're supposed to get these everything as objects. Well, not entirely true, but Python, yes, everything is an object. So then to support the concurrent programming, then these object-oriented languages have been updated to support synchronized objects, so that they package up the ugliness of these synchronization structures as much as they can, but only to a limited extent. Still, concurrent programming is not easy, even in the friendliest of languages. and you still have to rely on some use of structure. So monitor is kind of a nice try, and it is used in practice, but by itself is not enough. So you do need to supplement monitors with additional higher level language constructs. In this case, it's called condition variables. So you can think of condition variables as variables that have the weight and signal built into them. Okay, so you can use them, you can just use them just like any other variable, like assign and stick values and then modify, but you can also do the weight and signal on them. So what's a monitor anyway? Okay, think of it as more of an object that controls who gets to enter the monitor to perform some operation. Okay, so as any object, you have methods, right? You all know object-oriented programming. A function inside an object is called a method, right? Defined in a class, right? So these methods are really what you call to access these shared data structures. But it's not like anybody can just call these functions anytime. Instead, as part of calling these, and a lot of times you actually need to rely on these condition variables to gain entry into the monitor. But think of it this way. Condition variables oftentimes are used among these different methods as their way of synchronizing between them. Okay, but from the outside, they try to make it nice so that you just call a method, okay, into the monitor, and then it's ensured that only one process gets to make that call into the monitor at any time. So it excludes the other method call. So in Java, you may have seen methods that are synchronized with a synchronized keyword. Some of you may have seen that, may not have used it, but that's what it is. Okay, and so basically there's these entry queue into the monitor, and then inside there's these conditions, and then they control the access. Okay, and so variables for implementing the monitor oftentimes in terms of semaphores, and in fact different ways of using semaphore. You know, a semaphore can be used as a mutex if you initialize to 1, can be used for barrier if it's initialized to 0, right, enforcing the precedent ordering, and there could be a counting semaphore. So for variables, you can have a semaphore that's mutex, initialized to 1. And next, that's when you have a bunch of requests. You want to queue them up, and you want to enforce a total ordering. And that's why a barrier is used. Okay, so next is initialized to 0. And next count just counts how many are being queued up, waiting for entry. And then each procedure, or method really, the book calls them procedure, but think of these as method, will be replaced by, first, it's a wait on the mutex, the body of that method you want to do. And then there is the essentially trying to allow these queued up calls to execute within the same mutex. So mutex is only acquired once, but then whoever grabs it then calls and then that does the signal for the next, then they get to run, but they still hold the mutex until everybody waiting has finished, then it lifts that mutex. Okay, so that's what it does. And so this way it ensures mutual exclusion within the monitor, so upon calling a given method. Okay, and now condition variables. So in object-oriented programming, you know that you do the name of the object dot method call, right? And then method calls could be wait or signal, right? And a condition variable would actually also have these barriers and also the count. So similarly, whenever somebody does a wait, right, they're trying to gain entry. You increment the count, and then try to see if there's already somebody before you, and if there is, then you do the signal to next, otherwise signal to mutex. Otherwise, right, none, then you lift that mutex. On the signal, you check if count is greater than 0, and if count is greater than 0, then increment the next count. But signal the semaphore for x semaphore, the x being the name of that variable, so that then, because this is a barrier, it allows the x to be decremented, and then next count that gets decremented. So, but I mean, I'm not going to test you on this. This is just for your interest on how this one way that programming languages can implement. But the key point is really there are creative ways of using multiple semaphores to achieve, well, mutual exclusion as well as enforce the ordering in terms of a barrier, right? And also a counting semaphore. Okay, so resuming a process within the monitor, there's actually different semantics, and in fact, different languages may do it differently. So one is like if there's several processes queued on condition X, and then X dot signal gets executed, then which one should be resumed? Because there is the possibility of resuming X blocking whoever calling X dot signal, right? Because only one process is supposed to be in the monitor at a time, right? So that means you could try to unblock somebody, but you yourself get blocked. Or you could just say, well, I only registered the unblock, but I could keep running. There's different semantics there, and then there's names for these. And Java does it one way, the book does it a different way. I think book does more like what Python does. But anyway, there's reasons for doing one or the other. Not like one is absolutely just right. And first come, first serve may or may not be the right thing to do. Priority scheme may be more suitable, but the problem is anytime you start having priority, if you're not careful, you can have starvation. Okay? Anyway, so issue with monitors, there's also additional issues where depending on the kind of resource you're trying to access, maybe it corresponds to something with a file object or some other system resource that may require explicit permission. So here, we're only staying at the language level, okay? And so language level usually doesn't deal with or doesn't care much about any permission enforced at the OS level. But how can you be sure you do? And especially if you're sharing something that is system level object, right? So then that's kind of out of the scope of the language. And so that has to be put in there. So maybe if you use a library, that's okay. But if you're writing the code, you still have to be very careful. Now, still a process, even though monitor enforces like mutual exclusion on a particular call, so you don't have what's called reentrant call. Still, it can still hog a resource, and or you can still release a resource and never request it by mistake, or you could request same resource multiple times. So it's only solves some problem by making it a little easier to do, but then it doesn't support enough to be foolproof when it comes to reserving resources and returning them. So that's why I think monitors is kind of a still language level. I mean, you should know this concept when it comes to language because it's convenient and supported by a number of popular mainstream languages, but still you gotta know the lower level concept. The issues are still the same. Okay, so that is chapter 6, and next I'm gonna go into chapter 7, which used to be in the same chapter in the old edition of the textbook, but they split it out as a separate chapter. And this is important because later you actually get to try some of these examples, not the monitor one, but some of these basic examples in your own little threads package, and you'll get to see these. I think it's interesting. These are very simple examples, but they really highlight a lot of the good issues. So these are called classic synchronization problems. Classic means 1,000 years from now, people will still be studying these, I think. Anyway, so the purpose is really used for testing newly proposed synchronization schemes. Sometimes maybe the scheduling policy, or prioritizing scheme, who to wake up next, right? All these things. Okay, so these problems, there's 3 of them here. One is called bounded buffer problem, a lot like producer-consumer, and one is a more general one, readers-writers problem. And there's the dining philosopher problem. And oftentimes, dining philosopher is used for illustrating monitors. So bounded buffer problem is one where you don't have just a single shared variable. You actually have a buffer that's n deep. And then, so how do you do it? Well, there's actually one way to do this. You actually make 3 semaphores. One called mutex, one called full, one called empty. And so, full is not a barrier, sorry. But I guess way you could, if you call it barrier, it would be a very stretched interpretation. But okay, anyway. Mutex is for mutually exclusive access. And so that is when you want to do some amount of operation directly on that shared queue. Okay, and then there is semaphore for full and for empty. Okay, so what does a producer do? First, it does a wait on empty. Okay, so what does that do? So you can think of producers' resources that they want to request are the empty slots, right? If there are n empty slots, then that means the producer can produce up to n items without having to wait. Now, for the consumer, its resources are the full slots, right? Because it can consume up to n items, or assuming that's n, right? So then without having to wait. But if it runs out of, or if a producer runs out of empties, it keeps producing, runs out of empty slots, then you would expect the empty slots to be 0, right? So then beyond which additional request makes it negative and you have to wait. So, right, so that's why it does a wait on empty, because it's trying to check out, think of it, check out empty buffers slots, right? So, and it doesn't have to wait if empty slots are available, just like library, right? If there's book available, you don't have to wait. But it just calls wait anyway. And then once it has an empty buffer space, then what it does is try to get mutex. Why? Because you're modifying a shared data structure. So the mutex is a lock on the shared data structure. And then when it modifies it, does an enqueue, right? Updates all the variables, writes a buffer, and then signal means to return the resource to unlock, right? Unlock the mutex, and then signal full. So it said, oh, really? Okay, yes, that's right. Because when you do wait on empty, you basically grab this, but then you made available another instance, right? So you kind of return this resource not from the pool you check out, but to the one that the consumer wants, right? So, this says, tell the consumer, well, if you're waiting here, I just put in another item for you, okay? And the consumer does the opposite or the mirror of it. So instead of waiting on empty, like the producer, consumer will wait on full, right? So because consumer, if it already has a number of items, then okay, it doesn't even have to wait, right? So that's the false. So really, it's if it has item, then it doesn't wait. Then it just grabs. But if full is 0, then it has to wait. then so yeah, don't let the names confuse you. Know what it's trying to achieve. Okay, and then once it grabs an item from this full, once it really says, okay, check out by deducting from the full semaphore, then it needs to wait on the mutex before it can dequeue the buffer. Once it dequeues the buffer, unlock the mutex, then because it consumes, give the empty buffer back into as a resource for the producer. Okay, that's what signal does. So return an empty buffer back, which the producer would wait on. Okay, so that's how it works. So yeah, so these mutexes, mutex and then the semaphores, the names might not be ideal, but you know what they're supposed to do. Okay, so don't just take the names for their literal meaning. Know what they're supposed to do. Okay, and then so bounded buffer. If you line them up like this, produce next item, wait, empty, and then the empty could get this additional empty from the signal empty by the consumer, and then this wait mutex add, and then signal mutex. And signal, this will say, okay, I just made an item, and then the consumer waits on that semaphore, right? So, and context switch could happen anywhere except inside the atomic operation. Okay, so that was the bounded buffer. Readers, writers problem. Well, so you have readers and writers, and in fact, multiple readers at the same time. And when you have one or more readers, nobody should be writing. Okay, so that you can read something consistent. Now, writers, you can have multiple writers, but you allow only, well, at most one writer at a time. So this is not so symmetric, is it? Right? So this is kind of a funny thing. So this allows the readers, writers to share data, but then one reader or one writer excludes all the other writers, right? So that's not so symmetric. Okay, and so now you can have a few variations. One is readers don't wait unless the writer is accessing or writer has the highest priority, block out all readers. I mean, these are variations, but these can be done as minor adjustments. So, well, I think my time is about up. So I think I'm going to stop here. You could read ahead just so that you know your semaphores very well, because this all depends on your understanding of semaphores. Okay, so review your semaphores and be sure you understand the previous problem, the bounded buffer, and then I think then this one makes more sense. But this one is a little trickier than the bounded buffer one. Bottom line, semaphore. Really make sure you completely understand semaphore.